All right, here we go. Part 2 of our Unit 8 review series. We're going to pick up with implicit differentiation and related rates. So implicit differentiation just says you don't have to solve for y before you take the derivative. So pay attention to what you're taking the derivative with respect to. If I'm finding dy dx, whatever's on the bottom is the variable that you're taking the derivative with respect to. So the derivative of cosine squared of x with respect to x. And I'm going to rewrite the original problem as cosine of x squared plus sine of y squared. So derivative here, 2 times cosine of x to the first power, and then the derivative of cosine is negative sine of x. The derivative of sine of y squared would be, and then the derivative of x with respect to x is dx dx. I didn't write that because it's going to go away. But here, when I take the derivative and I get 2 sine of y to the first power times the derivative of sine of y, which is cosine of y, times the derivative of cosine of y, which is dy dx. The dy dx does not go away. And this whole thing equals the derivative of 1, which is 0. Now, a common mistake is that kids want to combine cosine x sine x with cosine y sine y. Cosine x and cosine y are completely different things, so don't combine them. So I'm going to move this term over to the right side. It's negative on the left side, so when I move it over to the right side, it's going to become positive. On the left side, I have 2 sine y cosine y dy dx. And I'm trying to find dy dx, so I'm going to divide both sides by 2 sine y cosine y. I'm not going to rewrite the whole thing again. Everything over here cancels. You can cancel out the 2's. Don't cancel the sines and the cosines because the variable on the inside is different. So your answer would be dy dx is cosine of x sine of x divided by cosine y sine y. So again, you don't have to solve for y first. Just take the derivative and pay attention to what you're taking the derivative with respect to. So that's what implicit differentiation refers to. Here's another problem. I want to find the equation of the line tangent, so I'm going to be using point slope form. The thing to keep in mind is, especially if they give you the entire point, so this is my x1 and my y1, I just need the slope at that point. So I don't need an equation for dy dx or for y prime or anything like that. I just need the slope at this one point. So derivative of sine is cosine. Derivative of xy is x times y prime plus y times x prime, which goes away. Derivative of x is 1. Derivative of 2y is 2y prime. Derivative of pi goes away. So I need to solve for y prime. But instead of solving for y prime now, I can just plug in my point. It will become so much easier. Cosine of 1 times pi over 2. And if I think about a cosine graph at pi over 2, cosine of pi over 2 is 0. So it doesn't really matter what I get when I plug in all this other stuff, because 0 times anything is going to be 0. So when I find y prime at this one point, add the 2y prime over, divide by 2. So y prime is a half. And that's all I needed. I needed y prime at this one point. So you can't plug in the point before you take the derivative, but as soon as you take the derivative, plug in the point if you only need the slope or the value of the derivative at that point. So my final answer would be y minus pi over 2 equals 1/2 times x minus 1. And this is why it's good to know the unit circle values. Even though technically you don't need to solve for this on a free response portion of the exam, it becomes so much easier if you know what it is. All right, I'm not going to work through the related rates problems again. There's tons of videos on them. I'm just going to talk about a couple of key points. Make sure you write an equation to start with. That equation needs to have the variable that you're going to be looking for. In this case, find the vertical velocity. So I need to make sure I have y in the equation. In this case, they gave me d theta dt. If you have a constant, you can plug it in before you take the derivative. So even though I know the y value at a specific point, when the angle of elevation is 45 degrees, we know what y is, but I don't want to plug that in before I take the derivative. I could plug it in here, but it ends up going away, so I don't need to plug it in. Make sure that on most of these related rate problems, you're going to be taking the derivative with respect to time. So the derivative of theta and the derivative of y, they both have a term when you take the derivative, d theta dt and dy dt. If you have questions about the related rates, go back and watch the videos either from this unit or unit 4 is going to have a lot of word problems on related rates. Extreme values was basically what we covered in unit 5. So when we talk about extreme values, we're talking about the maxes and the mins. We're talking about local maxes and mins, and then also absolute maxes and mins. Local maxes and mins will not happen at the endpoints, but you need to check the absolute max and mins because they could be at the endpoints. So check the endpoints because absolute extrema happen there. Maxes and mins, you'll be looking at the first derivative being equal to 0 primarily, also when the first derivative is undefined. The second derivative will help you with points of inflection or concavity. So the first derivative helps you with extrema. The first derivative also will tell you if the original function is increasing or decreasing. So f prime either being positive or negative tells you if f is increasing or decreasing. If I want to find the extrema, I'm looking at the first derivative. So I would solve for the first derivative here, and then wherever the first derivative is equal to 0. So I'd solve this equation, and we've already done that in another video. But wherever that equals to 0, those are the critical values. So in this case, 0, pi over 3, pi, 5 pi over 3, and 2 pi. These are all critical values. Critical values are places where you have a possible max or a min. You have to check to make sure that the derivative changes sign. So if the derivative goes from negative to positive, you have a local min. Now keep in mind that the minimum is the y value, not the x value. So the local minimum is at negative 1/4. Sorry, is negative 1/4, not is at negative 1/4. And then if the slope goes from positive to negative, if the derivative goes from positive to negative, then the original function has a max. And again, the max is the y value. To find the absolute max, you just look at all of the y values and look for the largest one, including the endpoints. Absolute min, same idea. The endpoints cannot be absolute max or min. They cannot be local max or min. So the local max or min, you have to be able to see a sign change, and you can't see a sign change at an endpoint. So those can't be a local max or min. Point of inflection is where the function changes from being concave up to concave down, or where the second derivative goes positive to negative or negative to positive. And that'll happen when the second derivative is 0 or when the second derivative is undefined. Now keep in mind that concave up really just means that the rate is increasing. Concave down means that the rate is decreasing. Concave up looks like part of a cup or an upward facing parabola. It doesn't have to be a parabola, but that's what it looks like. Concave down, you can think of a downward facing parabola. But concave up can also be like an exponential function. Concave down can be a logarithmic function. They don't have to be quadratics. And again, if we're going to answer questions about points of inflection or concavity, we're going to be looking at the second derivative. Maxes and mins are the first derivative, points of inflection are the second derivative. So if I wanted to find the extremes and the points of inflection, I would be looking at the first derivative and the second derivative. So the first derivative here would just be cosine of x. The second derivative would be negative sine of x. I want to know where they both equal 0. So the critical values, which are going to come from the first derivative, where cosine of x is equal to 0, would be pi over 2 and 3 pi over 2. The possible points of inflection, or the x values for those possible points of inflection, are when sine is equal to 0. In this case, we have negative sine, but it'll be equal to 0 at the same places. So when I make my table, I'm going to have x f of x, f prime of x, and f double prime of x. I need to make sure I put all my values in order. In this case, possible points of inflection were the endpoints. So 0, pi over 2, pi, 3 pi over 2, and then 2 pi. So I know the first derivative is 0 here and here, and it was just a cosine function. So cosine function goes positive, negative, positive. So I can go ahead and fill in that row. I know the second derivative was 0 here, here, and here. And then since it was negative sign, it went negative, positive. Instead of a regular sine function, would have been positive, negative. I don't need to find all the f of x values, just the ones where something interesting happens. Now in this case, something interesting happens at almost all of these points. So when sine is 0, then my f of x value is 3. I'm either adding or subtracting 1. So in this case, I'm adding 1 or subtracting 1. So my local max happens here. Here's my local max. The local max is 4. Local min is 2. Points of inflection happen when there's a sign change. So my point of inflection is here at pi 3. Notice that a point of inflection is a point. Local max and local min are just y values. And again, we need a sign change for a point of inflection. You can't have a point of inflection on the ends of the function either. So if our domain went further, these would also become points of inflection. But in this case, the only point of inflection is at pi 3. Okay, another thing we talked about in this unit was the second derivative test. So one way to see if it's a local max or local min is looking for the first derivative changing positive to negative for a max or negative to positive at a min. Another way to do it is to look at the second derivative. So let's look at the first derivative. Derivative of sine would be cosine. Derivative of negative cosine would be positive sine. And then does it have a local maximum at x equals 3 pi over 4? So all students take calculus. 3 pi over 4, we're over here. Sine's positive, cosine's negative, but they're both root 2 over 2. So f prime is 0. So far so good. And then let's look at the second derivative. So derivative of cosine would be negative sine. Then derivative of sine would be cosine. Negative sine would be negative root 2 over 2. Cosine would also be negative root 2 over 2. So this is a negative value. Since the second derivative is negative and the first derivative is 0, at this point, we do have a local maximum. Because if we think about it, the second derivative being negative means I'm concave down. First derivative being 0 means I'm flat. So if I'm flat, slope, and concave down, I have to be at a local max. So I never showed that the first derivative went positive to negative. That's the first derivative test. The second derivative test is where you show that the first derivative is 0 and the second derivative is negative for a max, and first derivative is 0, second derivative is positive if we were at a min. That's when the second derivative would be positive. I'm not going to go through optimization again. There's lots of videos. Anytime you're asked how to get the most or the max or the min or the least, you're going to be using optimization. So it's basically just word problems about finding extremes. So you're going to be finding the derivative, setting it equal to 0, and then proving that it's a max or a min. Remember to check endpoints, because on the AP exam, they'll try to trip you up by making the absolute max or min be at an endpoint. So that may not show up when the derivative's equal to 0. You have to check the endpoints as well. The last thing was derivatives of inverse functions. Basically, you just need to memorize this one formula and know how to use it. So if f and g are inverses, then the derivative of one function is the reciprocal of the derivative of the other function at their image points. If I wanted g prime of 7 and I have f, then I need the derivative, and then I need to know what x value makes f equal 7. So the work shown here or feel free to watch